sorry for all the disruption in the course schedule. I guess after spring break, there's going to be no more interruption. I'm going to lecture straight every week. So what I want to do today is wrap up, the first half of the course where you develop, connection between classical quantum path intervals, and you examine some basic quantum models like the Rotor model, the Ising model, and then you extended it to the Hubbard model, somewhat more realistic models, the boson-Hubbard model, and then last time Max discussed the electron-Hubbard model of the honeycomb bands. And there's some details left over for both that I want to cover to wrap up today. So I'll begin with the boson-Hubbard model and go back to chapter 8 in your notes. We'll go through the essential parts of chapter 8, where hopefully finally I explained to you to your satisfaction, why we call this a superfluid, why this has a superfluid phase, and what is superfluid mean. More precisely, actually, I explained what superconductivity means. I'll imagine the boson are charged and look at how they respond to electric field. Superfluidity is like helium-4 is a neutral boson, so there you have to, you have to worry about. It's a little more complicated issue of whether flowing helium gets slowed down by the resistance in the walls and so on. So it's a little more subtle, but it's basically the same idea. It's simpler to just discuss electrical charge transport in the presence of an electron. Okay, so here's a quick reminder. I'll come back to the electron-Hubbard model in the second part of my lecture today. This is the boson-Hubbard model that we've already discussed. We started with this operator formalism. We discussed coherent state path integrals, and then we introduced the Hubbard-Sutanovich transformation. So in the end, we ended up with this sort of path integral over two fields, psi and b. B was our underlying Bose operator, now elevated to a complex number which is fluctuating in space and time. And psi is a conjugate field. It's like the, when we did the Ising model, there was a magnetization and then there was an effect field acting on each side, and this is a similar thing, where B is the analog of the magnetization and psi is the analog of the field. And the reason for introducing psi is that it allows us to more efficiently talk about long distance correlations with B while properly accounting for the short distance interactions exactly. I mean, in principle, the nice thing about the path integral over the B is that it's completely local. It only involves one site. So just by thinking of it in Hamiltonian terms, we can compute any correlation function of B we want because we know all the states on a single site. Okay, we know all the energies and so on. All right, so we worked out the phase diagram of this kind of theory, and I won't dwell on all the details, but there was mu over u here, and w over u on this side, and there was some lobe-like structure where you had psi was equal to 0 inside the lobes. And these are the insulating lobes, for which we don't need to say much more because you can perturbation theory from the simple insulating state of one particle on each side or an integer number of particles on each side is still good. What I want to say more about is the structure of this phase here where psi is not equal to 0. So there's some average value of psi characterizing this phase. More precisely, of course, since psi changes the number of bosons, it's an operator that adds or removes a boson. If you have a system with a conserved number of particles, this automatically has to be 0 strictly speaking. So what we're really saying is that limit I minus j goes to infinity of psi star I psi j is equal to this quantity we call psi 1 squared. And the basic idea is that if I go really far apart, well, this can certainly be non-zero because it conserves the total for particles. But if I really go far apart, then it should be a local correlation function. What's happening here shouldn't really know about what's happening over there. So you can just factorize the average, and so you get average of psi, average of psi, and that's just using 1 squared. What's this? So this is the more precise definition of psi. So what I want to do today is now take this definition and argue that that implies it's a solution. So this is a more careful discussion of what the meaning of broken symmetry is. We've already discussed broken symmetry in the Ising model, but here it's a continuous symmetry, and that leads to some additional subtleties that I want to discuss. There's also some corresponding discussion about the Ising model is in the notes, but I won't discuss it. Okay. All right. So what we want to ultimately think about is not really the perfect system here, whose ground state wave function we can figure out. When we do an experiment, we're going to do something to perturb it. So we're going to have some space and time dependence at long distances, and we want to understand something about some general features of how this many-body quantum systems respond to very slowly varying long-time perturbations. Okay. So because of these external perturbations, we want to consider a situation in which psi itself, rather than approaching this constant value, has some space and time dependence, which is not constant. So what we're going to do is you're going to write psi is equal to, say, first of all, I'm going to take it has an amplitude and a phase. So let's just say it's some constant amplitude A times e to the I theta, and these are all functions of space and time. Working in imaginary time. In all my discussions up to the very end. And I'm going to assume the space label I becomes continuous. So, because I'm only going to look at longer variations. So what we would like is we want the structure. Let's say it's an effective Hamiltonian or effective action controlling a at theta at long distances and times. Well, you say, well, wait a minute, I already know what happens long distance. And this is the situation. Well, this is a quiescent closed condensate, and I want to know not just what's happening in the absolute ground state. I want to know something about some general variations close to the ground state. So here's a very complicated field theory, and I don't know how to solve this exactly. But I'm going to assume that this field theory is somewhere in this region. And the idea is kind of very much an RG idea. The approach is we're going to imagine doing an RG. We have the lattice scales, and we've shown you how you start integrating out the high momentum degrees of freedom in the tripolar field theory. And let's imagine we do the same thing here. I won't actually do it. It's good as a Gedanken expert to think that you're carrying out such a procedure. And then that defines what's called the effective action of quantum. So i.e., we integrate out all but the smallest momentum at frequency. It's a hard task to do this, and I won't actually do it, but I just want to see if I can use general considerations to understand what's happening. Okay, so once I do this, well, what is the effective action going to look like? Well, there's some potential for A fluctuations. So V of A, we can see looks something like this. Well, yeah, okay. A is the well, A has to be positive the way I defined it, right? So let me not, well, that's not consistent. So I'm going to have to draw a three-dimensional, make a better figure. So let's see. Psi is a complex number, and so it's the potential looks something like this. Here's the minimum psi, there's a circle over here. Okay, so this direction here is theta, and this direction this way is A. Okay, so independently of what's happening in the microscopic field, we know the potential must look like this. First of all, we know that if we rotate all the sides by a constant pace, by a constant angle, nothing changes. So the potential has to be flat, can't depend on theta. And then we know it has to have a minimum at some non-zero value because of this. Okay. Actually, eventually when we talk about two-dimensional systems in the Cosworth-Thorlestone vision, we'll see that this is still valid, this picture is still valid, although there's some subtlety in the application. This is not strictly, not quite correct. Let's consider the 3D or the zero temperature case 3D for now. Okay. So we integrate out everything. We want to know the structure of the long wavelength action. Okay. So, so without knowing anything, let me try to see how it's going to be constrained. So first of all, we'll say, A wants to sit at this minimum. And so any kind of perturbation in A is going to cost me energy. And any finite energy means there's some energy gap to those excitations. And I'm assuming I'm small, I'm well at a low, much lower energy. So I can basically ignore A fluctuations. So we just ignore A fluctuations. More precisely, what we really want to do is integrate out. We don't ignore it, we just integrate it out. We take into account it's some short distance correlation, some long distance effect, much like everything else that we have ignored or integrated out. Okay, so the only thing that's left is theta. So we're going to get some effective Lagrangian, L effective, and it's going to depend on theta of x and tau. Well, what is it going to be? Well, it can't depend on theta itself, so it can only depend on gradients of theta. Now, the theory we assume is invariant under time reversal and spatial convergence. So it can't have just one derivative of theta, one time derivative, one space derivative. So the minimum thing you can do is have two space and two time derivatives. And the only thing that's allowed is we write this way. We call it rho s over 2 drag theta squared. And the notes. Plus 1 over c squared. Plus a higher gradient. So this just follows from symmetry and the basic fact that everything is identical is invariant under a uniform plane of space. So every term here is invariant under psi I goes to psi I equals phi, and b I goes to vi equals phi. If I make this uniform change in phase, nothing changes there. And therefore, nothing in the effective action for this theta can also change. So theta is now some effective degree of freedom in this low energy effective action that I'm writing down here. Okay. So this is what I can see just by symmetry. I have two numbers, rho s and c, that are going to characterize my long distance fluctuation. So c is clearly a velocity just by dimensional. It's not the velocity of light, it's some number. It will turn out to be the velocity of sound in this fluid, whatever it is. And rho s is the more important quantity because for now it has many names. Sometimes, more probably, it should be called the helicity modulus. But sometimes it's called the stiffness, or some quite improperly the superfluid density. But it's really not a density. It So these two are, I think, acceptable. This is kind of confusing, although that's unfortunately also the more common name, but it's misleading. Okay. And the first thing we can see is what are the dimensions of rho s. So rho s is a number. It's a pure number that characterizes any single fluid, whether it's sitting on the lattice or not. It's a number you can, I'll show you how you can measure it, or if you had a fast computer, you can compute it. I've given you a prescription here of how to compute it. Do this very complicated exact RT. So in fact, this is almost impossible. So we'll come up with other ways to compute it. So for now, let's assume you know it, but let's, well, yeah, so we have this number here. Now what is the, first of all, what's the dimension of this number? So it doesn't depend on any lattice spacing. In principle, it's a unique number which determines the energy of long distance fluctuations. So here, you know, okay, h bar is in 1 everywhere, but really I should put the h bar there. So this is, if I put a 1 over h bar here, this is dimensions of 1 over energy, so the Lagrangian has to have dimensions of energy. And so rho s has to have energy times, there's two spatial gradients here. Whoops, okay. This way of writing things is not quite right because that was, okay, so there should then here be DDR. Right, so now it makes sense, okay. Now DDX. We have integrated over space and time is the local energy cost per unit volume per time interval. So now you have two dimensions of space here, two here. So the dimensions of rho s, has to have dimensions of energy times length to the 2 minus t, right? This is length to the d. So this 2 will cancel the two gradients here. Theta is dimensionless. And even the scale of theta is fixed. This I should have emphasized that. Theta, you can't rescale theta. Theta is uniquely fixed by the fact that theta plus 2 pi are equivalent. Okay? This is theta, so that e to the I, theta equals 2 pi is 1. That defines theta. You can't rescale it anymore. So theta is dimensionless, and as everybody will agree on the definition of theta. It has to have that property that e to the I theta is 1 for theta equals 2 pi. So that's the period of theta. Theta lives in a circle with period equals pi if you wish. So it's completely fixed. Everything else is fixed. So rho s is, everyone would agree on what the value is and what the dimensions are. Okay? And in 2 dimensions, there's the pure energy. And in 3 dimensions, it's energy over length. Okay? So I'll have units of, you know, the units of energy is joule, centimeter, whatever power. Okay? All right, so that's the very crucial quantity that we'd like to know more about. And eventually is related to the superfluid response and the London penetration depth, conductivity, and so on. All right, but before I turn to that connection, I want to present you with another definition of it, which is actually very useful and will kind of explain why they call it idioticity modulus, which at least in a computer simulation allows you to determine its value. So let me give you an alternative definition of rho s. So what I do is the following. Let me take my Bose-Hubbard model and put it in a box of very large size. Okay, so this is length L. And for simplicity, let's just take it length L in all directions, but of course that's not required. So here's my Bose-Hubbard model. Okay, and eventually I'm going to take it to the length goes to infinity. So now I can do 2 different calculations. You take your Bose-Hubbard model, you put it in a computer, and you compute its free energy. Just do whatever you like. Small U expansion, large U expansion, any your preferred method, or just brute force numerical number crunching. compute all its properties. But I'm going to ask you to compute its properties for two different boundary conditions. Okay. So the one will be the ordinary periodic boundary condition, and there will be a twisted boundary. Okay. So what I'm going to say is in the vertical direction, I'm always going to take periodic boundary conditions. So let's call this x and y, but y could be many dimensions. X is the dimension we're going to focus on. So along y, we take periodic boundary condition, which means that bi is equal to bi plus L and y hat. So it's periodic in this direction, and you will make this operator connection and then simulate that point. Okay. But along the x direction, I will take twisted boundary condition. And just so that you don't confuse it with that payload, I'm going to take the following boundary condition: bi is equal to bi plus L times x hat and e to the y. So what I'm going to do is I'm just going to put a small twist to the phase of my wave function. And numerically in a computer, it's quite easy to do. In real life, how would you do this? Well, you could imagine putting taking this direction. So that's this direction. It's a circular direction, putting a magnetic field through the hole of the torus, and it has the effect, if you know a little bit about the Aharonov-Bohm effect, of putting a phase factor and any particle that goes around that loop. So there's some Aharonov-Bohm phase factor that a particle going around in this direction will pick up. Okay. All right. But operationally, since most of us are theorists, we just put this boundary condition and solve them all. Okay, so what I ask for now is the change in energy. So I'm going to call this delta. And you can do this at finite temperatures too. So it's the free energy, the Helmholtz free energy. The free energy is phi not equal to 0. And free energy of phi equal to 0. So I ask you to compute this. So you go in and do this, and then you come back to the result, and we get a number. And then I say, increase double L, do it again, and then double L again, and keep doing it. And I ask you to look for the L dependence. And then you plot the L dependence to depend on L in a particular way. And if my guess is correct, it will depend on the following way. So what can we say about this? So first of all, let's think about what happens in the Mott insulator. So when you're in the Mott insulator, when we're here, well then, what is the state? Well, the ground state in the Mott insulator was, B1, say I have B1 dagger, n particles on the first side, B2 dagger, n particles on the second side, so on. That was my state. So all I've said is when I'm doing this twisted the lab goes on, I just change the phase of it a little bit. Okay. Well, I'll change the phase of the wave function, but I'm not going to change the energy at all. Because the bosons are localized. If you change the phase of one boson, it doesn't really care. It's not as if the boson here knows about the boson there, the phase of it, because they're all in basically orthogonal states. They're separated from each other. So you do this calculation, what you should find on the Mott insulator, this is a quantity that's going to decay exponentially. And it goes to infinity in the Mott insulator. That you can take as a definition of a Mott insulator. So this is how numerically you could just twist the boundary conditions, see how the energy changes. Of course, when they're really nearby, you'll see some effect. But here L is really tiny. But when L becomes large, eventually you won't care about the rest. So there's some characteristic length scale C, which is in fact the same correlation that we do computing the 2-point correlation. It's the same C that will appear here. Formally, in the Mott insulator, it doesn't care about twisted boundary. But this is actually, you can make an analogy to how you know the difference between liquid and a solid. So what's the real difference with liquid and solid is that when you try to shear a liquid, it doesn't care. Okay? So if you have a liquid in a box and you move the top to the bottom, you don't have to exert any force at all. It's just totally free. Whereas in a solid, it's going to cost you energy to shear. And it's going to depend on the length and the width of the walls and so on. So this is the analog of the shear modulus. It's not the compressible, it's the shear modulus, like the shear modulus. It's twisting things, twisting the phase of the wave function. And this is like in a liquid or a mod insulator. It just doesn't care what you do. Okay, but what about the superfluid? What is it going to do? Well, first of all, notice that this edge, assuming two are higher edges, on this edge, there's an infinite boundary here, even though it's purely boundary in the x direction. So this whatever boundary condition you're putting here have a lot of time to act everywhere. You want to minimize the energy in the boundary. So what are you going to do? Well, if you think in terms of the long wavelength theory, your theta is going to track phi. Your pose operator, theta is going to be essentially equal to phi. So what you're really doing is you're putting a twist in theta. You're doing the low energy effective action. You integrate out everything. There's some very slow, some very long distance twist you put. And the only thing that's going to be sensitive to it is this theta, this long wavelength theta fluctuation. So I can use this action to figure out what's going to happen. So here, if I take theta and I put a twist in theta from one end to the other, well, theta can take any value it wants. But clearly, the best thing for theta to do to minimize this energy is to just go slowly and linearly from one boundary to the other. So in the mod insulator, we're going to take or in the superfluid, all right. In the superfluid, we're going to take theta, it's going to be a function of x, so theta optimal. So theta is going to be not just constant everywhere. You could put theta constant. Suppose I put theta equals constant, and there won't be any bulk energy cost here. But then you'll pay a huge energy cost everywhere along this line. Okay. So you want the best theta that lowers the total free energy. And the best thing to do is, in fact, to spread out the twist. Okay, when you shear a solid, it's not just the last layer of atoms that moves. All the atoms move, and the shear is spread out throughout the solid. Okay, so that's the, well, you can prove this more formally by solving some differential equations. But you can sort of guess that theta optimal is just going to be phi times x over L. It's just going to go from 0 to 5 from one end to the other. Okay, so that's the optimal. We'll just plug it in here and figure out how much energy does that cost. Well, the delta F, you can see, rho S over 2 times L is V minus, because you're going to get 1 over L squared from here, from the gradient, and then you have to integrate over the entire volume, which will be L to the D. Okay. So, and then also this makes is consistent with our here, free energy is a free energy, that's total energy. Energy times length is 2 minus D, so the length will cancel out. And so there it is. So that's the definition, if you wish, of rho S. And you take this fluid, and this is the definition of rho S. So rho S is equal to 2 over there's a phi squared here, I'm sorry. There's a phi squared. So it's going to be a minimum, it's going to depend on phi quadratically, and the coefficient will be this. Delta phi over phi. And phi is presumed to be any angle less than less than pi. If phi is 2 pi, well, 2 pi is the same as 1, so nothing's going to happen. So here, I just assume that mod phi. Doesn't have to be small, it's only L that has to be. Since L is going to infinity, you can have a very, very slow twist, even for a finite angle. So that you can just take to be as a definition of OS. Okay, so if you take this as a definition, you just do your computer simulation, you get delta F. And in the mod insular, you get 0, because delta F will go exponentially as L, so that limit goes to 0. Whereas in the other phase, you should find, and that's requires some checking, but you can do any calculation you want. You can do numerics, or you can do epsilon expansion, 1 over n expansion, whatever you wish. You compute this quantity, you get some number, and now you can compute OS to your heart's delight to any accuracy you want. Okay. You don't have to do the RG. The RG was just a way of thinking that allowed us to write down this, to guess the structure of the answer. Okay. And this, for the particle theory, this is very analogous to what you do in the current Lagrangian for current symptom gradient QCD. It's something called F pi squared, which is the M log of OS. Whereas this is much simpler because it's simple to do in safety. Okay. So that's in fact, a more fundamental characterization of what a superfluid is. I characterize a superfluid here as one with a broken symmetry, with a non-zero condensate, psi not equal to 0. This is another definition. It turns out this is more general and more powerful. There is the famous case of 2 dimensions, or 1D goes into liquid with 0 temperature, which we will discuss after the break, where this is non-zero, but this is still 0. So this is a weaker definition. This is the more rigorous and better definition, having to do with twisted non-relations. Okay, so in the remainder of the discussion here, I'm only going to use this. So this discussion will apply even in these special cases like that, which are superfluids in this sense. Okay, questions? All right, so the next step is, as I said, to show that this means the superfluid, to figure out the effect of an external magnetic field, or external electromagnetic field, and look at the response due to an external field. There. So response. So I'm going to assume the bosons have charge Q. Q could be, anything. All right. So here's where we're going to actually use gauging invariance, and that's going to be an absolutely crucial determinant of all the properties. Okay. And it will show you how you actually measure rho as an experiment. And the simplest way of measuring it is using this definition. And then looking at the response of the magnetic field. So in the presence of a magnetic field, I'm going to assume you've seen this kind of thing before. This hopping term, B dagger I, Bj, and I want to just going to have the vector potential here. I want the scalar potential goes to B dagger I exponential IQ. Okay. I want to get all gauge bars and so on, right? Over H bar, and I put a CL just to not, so that's not confused with this C. This is the actual velocity of light in CGS units. If you're using MKS units, there is no factor of C here. But okay, my notes are in CGS units, so there it goes. So as the boson hops from one side to the next, it picks up this R of Ohm phase factor due to whatever electromagnetic field that you apply. And this is kind of the simplest phase factor that you need to have, because this is invariant in the gauge transformations. So the gauge invariance is the transformation. Okay. Where V of I goes to VI, dVi, we can call it vector first. Alpha I, so it's CL, and A goes to A plus rare. So if you make this transformation where the field generating the gauge transformation is both a function of space and time, then this coupling is invariant under this transformation. Okay, I'm sure you've seen this kind of thing before. And if you had an external magnetic field, the whole thing would be invariant under such transformation. And at the same time, the field psi is also must transform the same way for the action to be invariant that we can easily check. So e to the I alpha I q over h bar CL. And finally, theta then, because theta was defined using psi, theta goes to theta plus q over h bar CL. Okay, so this is all very useful because what we imagine now doing in principle is we put this external magnetic field on. It's not fluctuating, it's just some field we put on. Space dependent and maybe slowly time dependent. We're not integrating over it, it's some fixed space-time dependent field. And then we go the RG in its presence. Okay, I mean, in principle we can do it. We've got the action there, we just integrate out everything. There's a case floating around all over. It's a very complicated calculation. And I wouldn't want to do it. But in the end, I get some effective action. Now the effective action is dependent both on theta and also on A. And so now we can try to figure out, how does this effective action depend on A, or whatever it depends, it has to be invariant under this very fundamental gauge transformation. And therefore, my effective action, then you of course know then the unique answer. And notice there's no free parameters here. Everything is totally fixed. So Q here is some fundamental charge of the electron. These are all fundamental constants of nature. There's nothing more to choose other than the quantities I've already defined on the board. And the effective action then of theta, now I will also have an A in it, and I will only put the vector for that. So the only term that's consistent with this invariance, that this is the call it x or r, x. And you can drag theta minus q over h bar c. So that's the Lagrangian. Full Lagrangian for a superfluid, having coordinate superfluid, we're almost there. In the presence of external magnetic field, it is very simple here. Okay, so that's a very general and robust statement for any superfluid, any number of dimensions at low enough energies in the presence of a fixed electromagnetic field. There is some effective field theta, this phase theta that characterizes the superfluid, and it's just controlled by this very simple action. Yeah.
So here we only allow for the vector part of the vector potential, not the scalar.
Yeah, you can certainly put the scalar part in if you want it. But I won't need it for what I want to discuss today. Also, I should add, there's one criteria, one simple, we have assumed so far that A, one restriction that I haven't mentioned, that A is just fixed, the amplitude is fixed. Now there is a very important excitation where that doesn't hold, and that's what's called a vortex. You have a vortex where theta winds around by 2 pi, and then at the core of the vortex, A has to equal to 0. And then if you want to include vortices, then that, of course, complicates the the electrodynamics of superfluids and superconductors, which is a wonderful and rich subject, but right now we just ignore it. We're assuming we have conditions within the vortices. And vortices, of course, lead to degradation of superfluidity and so on. So this is like a perfect fluid with no vortices. So let me just back here, and we'll come back to vortices after the break. We'll talk about the 2D and so on. All right, so this is a very simple action, and from this I can compute everything with just a Gaussian theory. And if anything, we have learned in this course is how to work with Gaussian theories. Yeah.
The two A's are different, the amplitude and the vector potential?
Yes, absolutely.
Okay.
Thank you.
That's
There's nothing to do with each other at all.
right. So,
Let me put a vector here on these A's to emphasize that. Okay, so what do I, so here's my very simple theory. I have a very simple field. This is Gaussian, so I can compute lots of things. So among the things I want to compute is, say, the electrical current. So what is the electrical current? So J, this is the electromagnetic current. So I want to put the EM involved. Well, just by the definition of the, is just, if you go back to quantum mechanics and think about what the definition of electromagnetic current is, it's basically derivative of this Lagrangian with respect to A. That is the electromagnetic current. I guess it follows from what? It again follows from gauging variance, I suppose. That's the conserved current from Nuther's argument. We have a Lagrangian. This is going to be the current. Okay, so you can check it completely consistent with the usual definitions of quantum mechanics. And so in this case, I can take this derivative. So without any arbitrariness, my current is equal to then. Hopefully I got all the factors right here. It's rho as, oh, where's the H bar? Oh yeah. That's Q over H bar. That's grad theta minus Q over bar C. So the electrical current, the electromagnetic current is a gauge invariant quantity. It's something you can measure with your ammeter. It has some value. And this is also gauge invariant. And so this tells us now what theta gives us a physical meaning of theta. Gradients of theta carry current. But not strictly gradients of theta, you have to make it gauge invariant because theta is not a gauge invariant quantity. But this is not gauge invariant. Okay. All right, so now I have a very simple theory where I just take my partition function as this. I have this one Gaussian long Lagrangian field, and that's a theory I know how to compute things in. So partition function Z is just grad theta of x and tau of x and that was my effective action from the RT point of view, minus b tau, or bar, I guess, intercepted of theta and A. So there it is. Here's my theory. Everything's on the board, nothing under the rug. Here's the effective theory of any superfluid long distances. Here's the action on the Lagrangian, and here's my observable, the current. Okay. So of course, if I don't have any external electromagnetic field, the current is also zero. But in general, I will have some external magnetic field, and that can drive current. So this tells us how the superfluid will respond to current in the absence of vortices. Okay, and all of this just responds and depends on two crucial things. One is the existence of a helicity modulus being non-zero, and that means there's some low energy mode. I mean, there must be some long range effect or twist. And the second is gain unit, and nothing else. It's true for any superfluid, any dimension, any temperature. So, okay, so now we can do a few calculations. So let's compute the expectation of the electromagnetism in linear response in powers of A. You can of course do it to all order. I guess in this case, in fact, we don't even need to at this level, there's only linear term anyway, I think. That's correct. But if you had the full action, there are non-linear terms that principle could be. So what is the answer? Well, so this is J electromagnetic. So there's one term which is right here. Let me get all the signs right. Yeah, so that's minus. This is CL here. That's the right. Okay, so it's going to be. So this involves now doing some Gaussian integral. Okay, so we're just going to the linear response. Let me write it out. So J it's a vector, so it's a component A. So it's written as KAB, then JB. Oh, sorry. AB. Okay, so this A and B are just X, Y, Z here. These are vector components. So this is a linear response. The kind of thing you've done for the Ising model. You put a field and you get the response. Okay, here it's a little more complicated because you've got the field appearing in two places. The field appears here and it couples to theta in kind of a strange way. It couples linearly and quadratically. So they can throw out the quadratic term because it works within the response. And then the field comes in the current and it also comes without the current. So this KAV is going to have two contributions. Well, there will be one contribution which is right here. So that will be minus rho s q squared over h bar squared CL times delta AB. That's simply rewriting this term right here. That gives me this contribution. But then there's another contribution which is the other term. So that will be plus rho s q over h bar. Then the expectation of the grad theta. Well, expectation of grad theta is just 0 because if under spatial inversion, k goes to minus k, this is going to give me 0 when I integrate over k. But I have to expand this out. So when I expand this out, I get a term here. So the action L effective is equal to, let me go to Fourier space right away since you're all experts at it. It'll be rho s over 2 times theta squared times k squared plus omega squared over c squared. That comes from this term and this term. And then I have the cross term of these two. So minus rho s theta is k dot a. So there is a term linear in A which couples to k times theta, which is the same, but let me write it out as a dot grad theta. Okay, so when I expand this out, I'm going to pick up another factor of rho s, so it'll be rho s squared, and I'll get a grad theta here. This is now has to be evaluated at a equals 0. You see what I'm doing? I have a term which is linear in A. This term is up in the Lagrangian. I expand this Lagrangian to first order in A. And then the result of the current has a term linear in A. And the coefficient of this grad theta here is this grad theta over there. Okay? Traditional linear response calculation. Yes?
So what about the grad theta term in J?
Sorry?
What about the grad theta term? What happens to that?
Yeah, so there are two grad thetas here. This grad theta comes from here in the definition of the current. The other grad theta comes from linear response in the action.
But what about the term with just one grad theta? JEM equals the first term.
The one that's just 0. That's 0 because at A equals 0, our expectation of grad theta is 0. Just by spatial inversion.
Oh, so for small a.
Yeah, I'm expanding to the current. All right, so now this is just grad theta correlation function in this action. So you can work it all out. And the final result is this KAV is going to be equal to minus rho s q squared over h bar squared c times that's the linear response in the response of the current to a field. So this is some electromagnetic field that gives you current in the system, and the kernel of that response is this very simple answer. So the important thing to notice, it depends on nothing. This is CL here, and this is C. Depends just on rho s and C, which is the velocity of sound, and the velocity of light, and h bar, and q, all quantities you know. So that's why rho s is so funny, right? It just gets the, determines completely the response function for electromagnetism. And if you think about it a little bit, if you had some disorder and impurities, it's still true as long as you can coarse grain over long scales where the system is approximately homogeneous. It doesn't even require translation invariance in a sense. Rho s could be spaced in that a little bit, but as long as it's non-zero everywhere, this is still okay. So this definition I gave up here for rho s could work even in this dirty system. Okay. So now we're going to just focus on static response at zero frequency first. Yes?
So why do the k squared and the omega squared have the same sign?
I'm working Euclidean. Okay, I should really say omega and these are Matsubara frequencies. Everything is Euclidean.
Okay.
But at the very last step, we can change this to omega goes by omega. So there's no eyes in you. That's the advantage of Euclidean. All right, so let's just look at some of the consequences, which are also in the notes now. And once you have this k, you can now deduce various properties. So let's look at a static response. You apply some A, you wait a long time, and you look at what happens. The static response means omega equals 0. And that's good because then I don't have to worry about the scalar potential either. And in that case, then